haven't added those.
Okay. Good. So Martin will teach us some group theory.
Okay, so I'm not going to teach you a lot of group theory because I'm going to try to bypass like almost everything. So I'm going to talk about some construction of expanders, and essentially everything is going to come from group theory and a little bit of representation theory. But since I don't know any representation theory, I'm going to like completely ignore it and like push it in some small corners. Okay, so this is some kind of like what I plan to talk about. So I'm going to talk a little bit about expanders, but I think you know more than me, so I'm going to really skip this part. So almost everything is related to Kazhdan property T, so most of the talk is going to be introduction to property T, Kazhdan constants, how to compute them, some examples, and so on. And essentially, originally I only wanted to give like the second part of the talk, which is some relatively nice geometric argument, which I learned maybe a year ago. But Avi convinced me to give you some more background. So the second part is going to be relatively easy.
We'll give you another 2 hours now. Don't worry.
Okay.
Or in the best case.
Okay. So let's start about expander graphs. So my definition of expander is a very well-connected graph with small degree. And more precisely, you talk about epsilon expanders, and the graph is an epsilon expander if any set of vertices has a lot of edges. And you have to put some technical conditions, like not everything, because like otherwise everything is stupid. And you look at like the maximal epsilon with this property, and you call this thing an expanding constant of the graph.
This is the set of edges touching
I think this is set of vertices, edges. I don't really care about the exact constant, so think of whatever you want. For me, it doesn't make difference. For you guys, it makes a small difference, but okay. Just ignore it. And I usually care about a family of graphs which have a bounded degree, and then like all these things are completely irrelevant. And we're looking for families where the number of vertices goes to infinity, the degree stays more or less fixed, and the expanding constants are the same, or like uniformly bounded. So there are several equivalent definitions, and like one of them is like what you mentioned. If we fix the degree, there are 3 things which are equivalent. One is uniform bound for the Kazhdan, for the expanding constants. The second thing is uniform bound for the Chigre constant, which is more or less the same, but you count the number of edges leaving your set. And the third one, which I really care about, is spectral graph of the Laplacians. So you take the identity minus the normalized regency matrix, this is a positive definite operator, and you look for a spectral graph. And all of these conditions implies that if you take a random walk on the graph, you're going to get a relatively good mixing time. And the mixing time is going to be logarithmic in number of vertices. The constant depends on one of the constants here. So if you know any of these constants, you can like bound the other two. There is some kinds of inequalities which are a bit long, but not terribly long. So in general, if you allow the degree to go to infinity, things are a little bit more tricky. So these 3 conditions are not exactly equivalent. They're like almost equivalent, but you have to be a little bit more careful. And there are several definitions of expanding family when you don't fix the degree. And I'm not going to go there. However, I'm going to use things related to these constants like whenever the degree is not fixed. But this is more or less a technical tool. It's not going to be like part of the result in any way. Okay, so for me, there is only one way to produce graphs, and this is to take a group and take a K graph of a group. And in this case, there is another condition which is equivalent, which comes from the representation theory of the group, and this is essentially something related to property T and Kazhdan constants, which I'm going to introduce in a minute. And at least for me, a very basic question and very, very interesting question is the following. Suppose that you're given some family of groups which goes to infinity, when you can find a generating set of a fixed size such that the resulting K graphs become expanders. And this is an extremely difficult question And in some cases, it's known that it's possible. And essentially, the only cases where it's known, you have a big group with something like a property T. And then like you take all the quotients and like you're going to see in a minute why this thing works. There are only one or two cases where it's known that this is not possible. And essentially, this is if you take a solvable or nilpotent groups of fixed class of bigger and bigger sizes. And I don't know anything quite better than this one. And I think this was a result from the mid-90s, yeah. And it hasn't been improved since in any way.
So this is like some kind of a generalization of abelian groups?
Yeah, essentially saying that like with abelian groups you cannot do it. And like you just beef it up a little bit and go to solve.
But solvable groups can be expanded, only not if they are this fixed class, it's some technical condition that you know they are close enough, they are finite number of steps away from abelian.
Yeah.
Can you give an example of a non-abelian group of this class?
Yeah, fine group, like meta-abelian groups, nilpotent groups, Heisenberg groups, anything. Okay, so this is just a side remark, but okay. Okay, so what is Kazhdan constant? Okay, so first let's talk a little bit about representation theory. For me, all the representations are going to be unitary, which means that I'm going to have a Hilbert space, and the group is going to act by preserving the norm, or the distance, or the dot product, or any of these conditions. So what is important for me is the existence of almost invariant vectors. So if we have...
Before and just say what a representation is, so it's...
Okay, so a representation, this is just a map from the group into the set of unitary operators acting on the Hilbert space. So essentially like matrices. But for me, the Hilbert space is not finite dimensional, so they can be infinite matrices, and one have to be very careful. I'm using L2 norm. This is a Hilbert space, so everything is L2. And this is one of the problems why you have to work in characteristic 0. You cannot do this thing over finite fields. And in some sense, like, it's really interesting to try to generalize this theory to positive characteristic and to just try to do it over finite fields. And since you don't have the notion of a Hilbert space or anything similar, everything breaks down, and like practically everything is completely open. I think Avi knows way better than me. Okay, so what I do care about is the existence of almost invariant vectors. So precisely what it means, I have a subset of the group, which in many cases is going to be a generating set, and I call a vector almost invariant if every generator moves this vector a little bit. Some typo, okay. So if I take a vector, I apply a matrix to it, and it stays almost the same. And of course, I have some kind of epsilon, which is like my error term. So there is one easy way to produce almost invariant vectors. This is like take an invariant vector in the representation and just move it a little bit. And since the invariant vector is fixed by every element in the group, if you move it a little bit, then the perturbed vector is going to move by any generator and by any group element just a tiny bit, which is essentially twice the perturbation. Informally, property T is saying that this is the only way to produce almost invariant vectors. And more precisely, this is the following. We have a group, and we are looking, we fix a generating set. So for me, all the groups are going to be discrete. I'm not going to talk about like regroups, continuous groups, any topology, and so on. Just a side remark. You can generalize this thing to regroups, but I don't want to go there. So I fix a group, I fix a generating set, and I'm looking for a maximal epsilon such that if I have an almost invariant vector, this implies that I have an invariant vector somewhere in the representation. And usually this invariant vector has to be close to my almost invariant vector. And I'm looking for the maximal epsilon with this property. And I call this thing Kazhdan constant. So the group has property T if I have a non-trivial solution of this problem. I always have a trivial solution which says if I have a zero almost invariant vector, which means invariant vector, this implies the existence of invariant vectors. But I'm looking for some kind of a non-trivial statement. I'm looking that I can make like some small error and still claim that there exists an invariant vector.
You don't have a universal quantifier here over the unitary representation, so you should.
I should.
You should. So you want to say this
Uh,
for every
representation.
representation.
Okay, yeah, okay. I forgot to mention it. Okay, I have to put the quantifier for every representation.
So, or equivalently, for every representation without an invariant vector, there is also no.
Yeah, that's another equivalent. Okay, so there is another technical thing which I'm going to use, and this is called relative property T and relative Kazhdan constants. So I'm going to take this definition and modify it. So what I'm going to do is I'm going to fix a normal subgroup in my group G, and I'm saying, okay, I don't want an invariant vector for the big group because this is too strong condition. I only care about invariant vectors for this normal subgroup. And I do exactly the same thing. I look for maximal epsilon such that the existence of an epsilon almost invariant vector implies the existence of an H invariant vector.
For G or for H? The almost invariant vector is for
G.
for G.
Almost invariant vector is always with respect to the generating set, with respect to generating set S, which I fix.
Oh, okay.
Actually, I'm not going to fix it. Yeah. So essentially, this thing is I take H to be equals to G.
Why do you assume H to be normal?
The problem is, if my subgroup is not normal, it may happen that almost all representations have H invariant vectors. And this is going to cause a lot of trouble. Equivalently, I can modify this definition and say there exists an H invariant vector which is close to my almost invariant vector, and quantify this thing in a different way. Okay, different people have different notion of relative property T. So if you have normal subgroups, everything agrees. If you don't have normal subgroups, like you have to be careful which definition you're using and so on. Some people even say, okay, we don't really care about subgroups, we can talk about semi-groups or just big subsets and so on. I just don't want to go there.
Maybe just a trivial comment. If something is invariant completely invariant with respect to the generating set of a group, then it's invariant with respect of the whole group. But that statement is not necessarily true for the, almost invariant.
Yeah, that's essentially like what this whole business is. And another comment which I want to mention is that in this part, if I can deduce that there exists an invariant vector with respect to the whole group, my set S have to be a generating set. I don't really have any choice. If the set S is not a generating set, this thing is completely false. Here, S does not need to be a generating set. And in many cases, I'm going to talk about some S which is like relatively small. It's not going to generate the whole group. Again, this is like a technical point which I'm going to ignore.
This thing will allow you to actually construct.
Okay, so historically, this is like how the whole machinery of property T started. Of course, it started with regroups, not with discrete groups and so on, but relative property T was like a big part of this machinery, and like the only results which do not use any form of relative property T appeared like a couple of years ago, late 90s, I think. Yeah.
How is the definition dependent on the specific generating set?
Okay, so it's a classical result, and you're going to see it in a minute, that if the group is finitely generated, this part, property T, is independent on the generating set. If I pick any finite generating set, I'm going to get the same thing. However, the value of the Kazhdan constant is going to change significantly.
So I don't understand. I mean, how
The definition of almost invariant is with respect to S.
so what was almost invariant?
Okay, almost invariant vector is a vector such that for any generator, GV minus V is small. I don't insist this thing to be true for any element in the group. If I put any element in the group, this is going to be like a very strong statement which you cannot check it in reasonable amount of time.
Can you go through that definition again? So G you're thinking of as the matrix corresponding to the group element.
So G is the matrix corresponding to the
And V is a vector.
V is a vector.
So GV is a
GV minus V is how far I move this vector. and I just put the L2 norm, and this is a typo, and this has to be small.
Okay, that's the one I was worried about.
Okay, sorry.
It's not that.
Yeah, it shouldn't be there. I cannot erase it. And okay, another comment here, once you start asking, when I talk about almost invariant vectors, I usually assume that my vector v is unit. I want to normalize it. Because if you take a very small vector, it's obviously almost invariant. And I don't want to just go into this kind of mess. And another equivalent thing is to normalize it, but I'm just lazy.
So
Yeah,
like you would take a big vector also. Maybe that v should be multiplying. It should be
Yeah,
epsilon
so
times the norm of v.
That's why.
Yeah, at some point it was here, but okay, I just...
Otherwise, it might take a big vector and it would be almost invariant.
No, you can take a very small vector and it's almost invariant, not big one.
Okay.
Okay. Okay, at least you're following, you're asking questions, so that's a good sign. Okay, so I went to this thing. And okay, let's just mention a couple of groups with property T, and then I'm going to discuss a little bit more how to prove it. So first thing, which more or less falls from the definition, is that any finite group has property T. And the reason is that a finite group has essentially finite remaining representations. So you have only finite remaining representation without invariant vectors. And for each of these representations, you have like a finite dimensional representation. You're just looking for something on a unit sphere, and like just compactness argument tells you that there is a universal bound, which is how close you can keep every element from the generators. Another thing I want to mention is that
But the finite bound you get on the constant depends on the size of the group.
yeah, that's what I'm saying. That I was going to say. Even if you know that a group has property T because it's finite for essentially trivial reasons, this doesn't help you to compute the Kazhdan constant. And actually, like even estimating the Kazhdan constant for some finite groups, it's like quite a difficult thing. And there are only like 5 or 6 examples where you know the exact value of the Kazhdan constant, not just bounds for it.
So if you have a family of groups where the constant is, is where it's omega 1 or theta 1 as n goes to infinity, does that imply the group has good indicator?
Yeah, that's what I'm going to tell you in a minute.
I just want to stress the first point that is just like saying that in a connected graph you have a spectral gap. Unfortunately, this spectral gap is like 1 over the number of vertices, so it's not really meaningful at this point.
Yeah, that's what, okay. So the second classical example, which is essentially like the motivating example for the whole theory, is if you take high rank Lie group and you take a lattice in it, it's going to have property T. And for me, the typical example is SLNZ.
Yeah. And so rank is n.
Rank is n minus 1, so for SLNZ I need n to be at least 3.
So what SLNZ is matrices with
Determinant 1 with integer n.
Okay, so another thing which just came around in the last maybe 20 years, if you take a random group in some meaningful category, so take like a random presentation, you're going to get group with property T. For computer science people, this is completely useless because these groups usually do not have any finite quotients, so you cannot use them for meaningful things. So what I was going to say, and that's exactly what you asked, if I have an infinite group with property T, I can take its finite quotients, I can take a generating set of the group, project it to a generating set of each finite quotient. The Kazhdan constant is going to behave nicely with respect to projections, and as a result I'm going to get a family of expanders. An equivalent thing is if I have a family of finite groups with a fixed generating set, and I have a universal bound for the Kazhdan constants, this gives me family of expanders. And of course I need to fix the size of the generating set, otherwise things can become a little bit crazy.
So how are you constructing the expanders given these groups?
If I have a group with property T, I fix a generating set for the group, and I look for all finite quotients of the group. So this gives me a family of finite groups. In each of them I can take the generating set of the big group and project it to a generating set of the quotient, and take the carry graph.
So the canonical example is we look at SLNZ, let's say.
Okay, let me write it down.
You have it.
No, I don't have it, but I'm going to put it on the board because like you're asking. So a typical example. Which one is the white?
No, the other side of the down, yeah. No, left.
Okay. So a typical example is you take SL and Z. You project it to SL and FP. Now you take a generating set S, and you project it to, say, a new generating set S bar. So you can think of like all elementary matrices with plus or minus one of the diagonal. And when you project them, they more or less stay the same. And now you take the Kerry graph.
Project means do what we.
Yeah. And now you take the Kerry graph of SL and FP with respect to this generating set. And these guys are expanders. Okay.
Not only are they expanders, if you have Kazhdan constant epsilon there, then you will get, they will be essentially epsilon expanders. Epsilon over 2.
I'm not sure. Maybe you have to square the constant. There is some function which allows you to, if you know the Kazhdan constant here, you can compute the expanding constant here.
If you look at the spectral gap, it will remain the same. It will be that if you have Kazhdan constant,
Sure.
epsilon, then the spectral gap of this Kerry graph will be epsilon.
Sure.
Now,
Sure. Sure. For the spectral graph, everything is going to stay the same. For the okay.
So is the spectral gap exactly the same?
Exactly the same.
No, it's not it's not exactly the same. It's not exactly the same. When you do projection, the spectral gap can go up a little bit.
There is a factor of the size of the set.
No, I meant for finite groups. So you take a finite group.
Okay, just give me a second, and like you're going to see like.
Okay.
There is a factor of the size of the generating set.
So in fact,
No, it depends on the definition.
there are like several definitions of Kazhdan. Okay.
Sir, I was completely, how is the property related to the spectral, like in the first place? I mean,
Okay.
what's the relation?
Okay, in the second. Okay, just give me a minute. Okay, so in fact there are several definitions of Kazhdan constants, which are like in some sense equivalent. You can pass from one to the other by just putting some constant, maybe squaring something, and so on. And the one I started with is the following. So you take an infimum over all representations without invariant vectors. Then you take infimum over all unit vectors or all non-zero vectors. And then you take maximum over the generating set and how far you move this vector by the generator. So this is equivalent to the definition I just put before. Yep.
Does it matter that it's representations without invariant vectors and not irreducible representations?
It matters. In this definition, it matters, and you have to take all representations. If you look at representation without irreducible representation, you have to put something like 1 over the size of the generating set. You have to put a correction factor, a little bit. So in the limit case, if you just want to care about whether this thing is positive or not, there is no difference. But in general, you have to be a little bit more careful. Okay, so there is another thing you can do, which is instead of taking a maximum here, you can take the average. So instead of taking a maximum over the generating set, you're taking average over the generating set and like square it in order to make it behave nicely. And now here, this thing is exactly the spectral gap of the Laplacian, up to some factor which is probably 2, because I messed it up a little bit. And also in this definition, you can take only irreducible representations. You know that the infimum is achieved as an irreducible representation. Okay, so in some sense, this definition is better because you can increase the generating set and everything is going to like behave nicely. When you increase S, the maximum is going to go up, so the Kazhdan constant is going to go up. Here, when you increase the generating set, you have no idea what's going on in general. If you just increase it a lot, I'm not just saying like put an extra element or two. But in some cases, like I prefer to work with this definition. In some cases, I prefer to work with this definition. And it's very easy to go from this one to this one. You just put some bound which depends on the size of the generating set and some square. Okay, but something which is relatively important is in everything I'm going to do is I'm going to change my generating set. And although if I'm going to start with a small generating set, at some point I'm going to work with a very big generating set where the size is not going to be bounded. And then these two definitions are completely different. So the connection with the spectral graph is here. So this is here the spectrum graph, yeah?
The first one is not really meaningful when the generating set is large?
All of them are meaningful, they're just not equivalent.
The connection, just to
Okay.
point out, you are not going to do it. The connection to the spectral gap in the second definition is not mysterious at all. It's just a change of basis of the adjacency matrix of the graph. Just the change of basis that corresponds to which gives you the irreducible representation. So once you change the basis, this stands out.
But you said you don't take only reducible.
For this one,
Oh,
I take any representation. For this one, I also don't take only irreducible, but it's very easy to see that it's enough to take irreducible representations. So for the second definition, like you can just restrict yourself to only irreducible representations. And that's really useful if you know the set of all irreducible representations, it's relatively easy to check it. For example, if the group is Sabirian, it's very easy to compute this kind of stuff because you go over the.
So let me see if I'm following, just to sketch it. So for in the Cayley graph, for every generating element, you have a set of edges, which is a permutation. That gives you a permutation matrix on the nodes of the graph.
Yeah.
Which are also the elements of the group. And so you can think of the adjacency matrix for the Cayley graph as you're summing up these permutation matrices. Okay. And then something, an invariant
This representation has invariant vectors.
Right,
For example, the
but
O1
it's
vector.
but that's gonna, the invariant vectors are there'll be vectors with eigenvalue 1.
Yeah, the constant
For
vectors
eigenvectors for the eigenvalue 1 for the adjacency matrix. Maybe not all of them will be invariants, I'm not sure. But the constant 1 will be. And so then, say we mod out by that. So we're looking at the subspace of
Yeah.
things.
Okay, you have.
Sum is 0.
Yeah. And you have only one invariant vector, this is like the constant one, and when you mod it out by it, then you have a representation without invariant vectors, and you're looking for what's going on there.
Right.
So this is essentially your.
You look at this, and in that space is the eigenvector for the second largest eigenvalue. If that's going to be, presume in this sense, that's going to be an almost invariant in the sum of
yeah.
the sense of the sum.
So essentially, that's correct. So the infimum here is achieved when you take the eigenvector for the second largest eigenvalue. So something which maybe you care about is I don't care whether -1 is an eigenvalue or not. So for me, I have bipartite graphs which are expanders. This is not a problem. So there are ways to fix this thing. I just don't want to do it. Okay, so let's talk a little bit how one can compute Kazhdan constants and where this whole machinery comes from. Okay, so let's start with one trivial bound. So for me, the trivial bound is when you take a finite group and take the generating set to be the whole group. So then the Kazhdan constant is essentially 1. So if I take the other Kazhdan constant, it's going to be equal to 2. And there are several ways to see it. Let's ignore this thing for a moment, and this thing for a moment. For you, the easiest way to see it is to say, okay, like we're getting a complete graph. It's very easy to compute the spectral of the adjacency matrix for this graph. So essentially you have 1 and you have everything else is 0. So the spectral gap is very big. And that's what you have. If you want to phrase it in the language of like unitary representations, what you have is you have a vector which is moved by every generator a little bit, but a little bit is like square root of 2. And essentially, this tells you that the whole orbit of this vector is inside some half space. So when you take the average of the orbit, you're going to get a non-zero vector, which is going to be invariant because it's average of invariant set. But OK, maybe that was like the better definition, explanation for it. OK, so that's completely useless thing because like you don't want to construct expanders by taking complete graphs. OK, so what is the next thing? So the next 2 slides allows me to change the generating set and still maintain some control over the Kazhdan constant. OK, so the first thing is the following. I take a generating set. I build a new generating set which consists of all short products, and then I can relate the Kazhdan constants. So this set is much, much bigger. So you expect the Kazhdan constant to be much larger. However, I can control this Kazhdan constant with respect to this one. So in the language of graphs, what this thing is saying is that if you have a graph, which is an expander, when you take like all the edges which are like paths of rank up to 5, again you have an expander and you can like relate the expanding constants in a reasonable way. So in the language of almost invariant vectors, if you have a vector which is moved a little bit by every generator, this vector cannot be moved very far by product of 5 generators. And as expected, you have to pay some price, and the price is like this 1 over k. OK, so the next slide is essentially what for me is like the most useful way to change generating set. And like it allows you to do a very ridiculous thing to the generating set. If you have a normal subgroup, and if we know the relative Kazhdan constant, what we can do is we can just throw the whole normal subgroup in the generating set. So for me, the easiest way to translate this thing into graph theory is something like zigzag products. I'm not sure that this is exactly zigzag products, but it's like it falls from zigzag construction.
Is that equivalent to sort of looking at the graph where you're modding out by age? You know, so you're
Essentially,
with the same.
Essentially, this thing is like you're modding out by age.
Yeah.
This is the relative Kazhdan constant. This is when you do not.
G dot, G, that's the relative.
So this is the relative Kazhdan constant, which says that like if I have an almost invariant vector, this implies the existence of an H invariant vector. And when you quantify this thing, it says that if you have a vector which is almost invariant with respect to S, it's very close to H invariant vector. And therefore, the whole normal subgroup H moves this vector a little bit. And that's
What is the G dot, H dot?
this one?
Yeah.
So this is the relative Kazhdan constant, which says the following. If I have a vector which is almost invariant with respect to S, there have to be an H invariant vector which is nearby.
Okay.
And
Or
this near.
you look for spaces that don't have H invariant
Yeah.
vectors, and look for the.
And that's one of the reasons why I want to have a normal subgroup, because I can quotient by the space of H invariant vectors, and this is going to be a G representation.
So the proof of this is trivial, right?
Yeah, that's the proof.
So you can read your reading.
Yeah, the proof is very trivial. There is nothing deep here. And that's why I'm not saying that this is exactly zigzag products, because the proof of zigzag products is not trivial, or at least it's not that trivial. But this is like, at least for me, they seem very connected.
For the case where G is a semi-direct product of H and another group, then there's also a zigzag product.
Yeah, I think that's like the best analog, which is there. But I don't think the proof even for this zigzag product, you can fit it on a couple of lines like this one. Okay, so another thing I want to do, and the reason is some of the groups I'm going to play with, like this group, are going to be simple, and they don't have a lot of normal subgroups, so I cannot really apply this stuff. So I can do the following. Suppose that I have a group, And inside this group, I have many pairs of like a normal subgroup and a normal subgroup in it. And now if I have, for each pair, I have some generating set, and I have a very good estimate for this relative Kazhdan constant, then I can like put everything together and essentially like take the representation of the big group. For big parts of this representation, ignore the action of the whole group, but just look at the action of the group Ni, and then apply this result.
So Ni's are not normal. HI's are normal.
Hi is normal in Ni,
Ni, which is some subgroup.
which is some kind of subgroup. So this tells me that if I know a lot of relative Kazhdan constants and a lot of groups can be embedded in my group G, then I can control the Kazhdan constants by throwing big subgroups in the generating set. So here I'm taking like union of subgroups, and these subgroups can be quite big. So in the example here, so this generating set consists of like elementary matrices with plus or minus 1 of the diagonal. I'm going to take the root subgroups, which is like all elementary matrices with anything of the diagonal, and I'm just going to take the union. So this is going to. I'm going to show it. I'm just. That's what I'm. Yeah. I'm.
G, or do you mean union of Ni?
Which one?
In the last statement?
So I can control the Kazhdan constant of G with respect to the union of Si. So in each of these guys here, I have a generating set. And here, I can put the generating set, which is the union of HIs, which I don't know.
I think the question is, are you assuming implicitly that G, that the union of the Ni's is all of G?
No, I'm not assuming that the union of Ni's is all of G. Here, I'm assuming that the union of HIs generates G, because otherwise this is going to be 0, and this is going to be a very stupid inequality.
But that implies it, right?
No, it doesn't imply. No, I'm not saying that the union is everything. I'm saying they generate it,
Okay. Right.
which is a very mild condition.
Okay. Sorry.
So if I want to be precise, I can throw here also the union of SIs, but I'm just lazy and I don't want to just
That
mess.
mean product of the Ni's.
Every element in the group G can be written as a product of elements from HIs. But typically, HI is going to contain, the union of SIs is going to be inside the union of HI, so this is going to be like a very mild condition.
It would be interesting when the union of the SIs does generate G.
Yeah, okay, otherwise it's like both of them are 0, so this is not a very interesting condition. Okay, so at some point I have to use some representation theory, and that's the representation theory which I'm going to just use, and I'm going to hide it in one theorem. And so this theorem started like, I think in the early 90s by Mark Berger, who proved some kind of weak form of it. Then Yehuda generalized it, and I generalized it a little bit more. And what we have is the following. Suppose that you have any associative ring, which is finitely generated by a bunch of elements. I have a generator of the ring. I assume that the ring has 1, so the ring is like reasonable. And I look at the following subgroup of GL3R. So I look at like the matrices, which are like, I have 2 by 2 block and something here. So this group naturally splits as a semi-direct product. I have GL2 semi-direct product with this guy. Okay.
So you're not going to define it, I assume semi-direct product. I'm not sure everybody knows, so we'll see if you need it. So, or this will be a black box.
This is going to be a black box. That's why I put the group in this form, so that like people are not going to be completely confused. Okay, so this group contains a normal subgroup where I put the identity matrix here and like anything over here. And what this thing is saying that I can estimate the relative Kazhdan constant, and I have a nice bound which is independent on the ring. It depends a little bit on the generating set, on the size of the generating set. And what is F, this generating set here? This is something like a natural generating set for this group. So what you do is you take 2 by 2 elementary matrices where you put plus or minus 1 or plus or minus generator of the ring of the diagonal, or you put 1 here or 1 here, and that's it. So you have a relatively small generating set. I don't know how many elements you have.
Put 1 here, you put 0. In the places you don't specify.
Yeah, in the okay, you put 0 or 1.
Okay.
So here, for example, on the diagram, you have to put 1s. You put the obvious thing. So essentially, these are like the obvious elements in this group, which have some decent chance of generating the group. In many cases, they do not generate the group. I don't really care. That's like one of the things with the relative Kazhdan constants. They're going to generate this piece R square. They may not generate this whole GL2. Okay, so what? That's not a big deal for me. Okay. What is the proof? Okay, I'm not going to say anything more about the proof. The proof goes to the fact that here, R2, essentially, I'm seeing the additive structure of the ring R. So this thing is going to be an abelian group, and I know very well all the representations of this abelian group. So I know the unitary dual, and what you can do is like you can just do something for each unitary representation. So you have to put some measure theory and like put almost invariant measures, spray a little bit of combinatorics, but okay. That's not difficult. It's not a.
These are characters. I mean,
Yeah. Okay. This is like a character. Well, the group is abelian. Essentially, you're working with a abelian group, and that's what saves you. For me, this is not a hard representation theory. This is just playing with some game with some measure sets and like cutting a torus into several pieces and so on. Okay, I don't want to go there. It's going to be technical.
It's a way to get exactly the type of thing you need, some relative Kazhdan property.
So essentially, this is the type of things I want to need. I want to push the representation theory in some kind of like small corner. The representation theory is going to be relatively easy, and you can do it. And just believe me that like this is the
The structure of this result is that exactly you have a normal subgroup and a bigger group.
Yep.
You have a relative Kazhdan.
Yep. Okay, so now let's. Okay, I need another couple of results.
Just to know where you are going. You are going to infer from this later Kazhdan constant for GLR3.
Yes.
XLR3.
Yeah, so in a moment I'm going to use this thing to compute the Kazhdan constant for this one. But before doing this, I want to go into another piece of group theory, which is called bounded generation. And this is a very strange property, which is almost not understood. Like, it's a very basic question, and practically nothing is known, except a few examples. Okay, so what is a bounded generation? So there are many ways to say it. So what I'm going to do here is I'm going to cheat a little bit. So I have a group, and I'm going to fix a generating set, but it's not just a set. It's ordered multiset. So I roll repetition. I just list some elements in the group in some order. And I said that like this ordered multiset boundary generate the group if I can write any element in the group as product of powers of elements here, but I cannot change the order. I can just go only once through this thing. So essentially, this is saying I can write any element in the group as a product of k powers from elements in my set, nothing else. And of course, these powers have to be some integers. I don't claim anything about uniqueness. I don't know any non-trivial example of a non-abelian group where you have uniqueness or anything like this. But okay, this is just existence. Also, I said this is a very strong property. It implies a lot of strange things about the group. And it was open. Okay, this whole machinery started in the 80s by a result of character and care, which I'm going to mention in a moment. But it's completely open which groups has this property or which do not have it.
So when you say a group has it, you mean there exists a multiset?
There exists a so a group is said to be boundary generate if there exists a multiset such that you have this property.
Just to point out something that's quite easy. For every finite group, let's say of size n, there is such a multiset of size log n, which does it for every group. And that's
Okay.
And even with the power 0 and 1,
Okay.
that's easy.
For me, an easy thing is you have a multiset of size n. But like you want to be a little bit more greedy and like put some logarithm, but okay.
What you said is trivial, and this is, if you want the exact length, it can be 1 times log n plus 1 times log n. If you but I'm just pointing out, so you want k to be a constant independent of the, well, so you want it to be small. For every group, well, I don't know how it is. It's a fact that you can take log n, a multiset of log n elements, let's say 2 log n elements, and then every element of the group is this ordered product of these multiset elements where the AIs are either zeros or ones. It's like a cube.
So you just say rarely said the space elements.
I don't know if
No, I'm not going to prove it. That was like some.
Because
that
we
was-
are talking about special groups. I just wanted to point out that there is a general fact in which the set is large.
Okay, the only thing I was going to mention that like for finite groups, this is everything. This is obvious, and like I only care about infinite groups. But yeah.
You use an ordered multiset, you allow, like, if an element appears twice, it can appear at different places in the order that are adjacent. That's why you use a multiset in that set.
Yeah, they can be, yeah. This is just sequence of elements in the group of rank k.
So is that SLNZ?
Yeah, that was like what I'm going to go there. This is a result by Carter and Kayor, which says that any matrix in SLNZ for n more than 3, of course I forgot to mention it, can be written as a product of some fixed number, which is like, that's some kind of decent bound, to n squared plus 100, elementary matrices. And by elementary matrices, I mean a matrix where you have like once on the diagonal, everything else is 0, and you have something sitting somewhere in one of the other places. So this was like relatively surprising result when this thing was found in 82, 83. Right now there are a couple of proofs of this thing. Most of them are quite explicit and gives you something which, like, if you're given an element, you can write it matrices such that the product is equal to this one. But in order to do this thing, you have to do a lot of crazy things, like find primes in arithmetic progressions, find like things which are like known to exist from number theory, but are relatively hard to just do it by hand.
So if you replace them with the field with rational numbers, then it's trivial, right? It's just.
Yeah, that was okay. There are a couple of like slides things I'm going to mention. So there are a couple of steps in the proofs. In the proof, which are like relatively important. The first one is reduction from SLN to SLN minus 1. And this reduction is relatively easy. You look at the last column of the matrix. So the GCD of these guys is equal to 1. And then you can like essentially take one of them and add suitable multiples of the other guys to make this thing prime. Once you make one of the entries prime, you can like easily reduce the matrix and like kill the whole column and make 0, 0, 1 in the last column. And once you make 0, 0, 1 in the last column, like a few more steps gives you reduction to SLN minus 1 sitting in the corner. So that was like relatively easy step. This works from, you can go down to SL2. You cannot go down from SL2 to SL1 because SL1 is too small for practical purposes. And the next step, which is like the really heart of the problem, is that if you take any matrix in SL2Z, if you look at like SL2Z as a group, this is practically a free group. There is no way you can write any element as a product of fixed number of elementary matrices. Simply, this is false. However, if you enlarge the group and you're allowed to use elementary matrices from SL3Z, which is slightly bigger, then you can do it. And this thing essentially says that like you can write any element in SO2Z as a product of about 100 elementary matrices coming from SO3Z.
But you were also restricting the order in which these arise.
Yeah.
Okay.
This theorem is
I mean, it's a constant, so you can take.
It's a constant, so you can take a permutation. Okay.
yeah, but that's when is which one?
Okay, so actually in this theorem, I'm not saying anything about the order. I'm not saying that this is a bounded generation.
No, but it implies, right?
It implies bounded generation. So,
All possible permutations.
okay, you're right.
But then the number of matrices is more than the number of elements. Oh,
No, the group is infinite. It's going to be a constant which depends on n. I really don't care how it depends on n. Actually, it's going to be quadratic, but that's the important thing.
But still, the number of elementary matrices is still infinite. So
No,
Sure.
It's about once you fix this thing, it's like.
It has one of the diagonal.
just has ones on
You can read the statement of bounded generation two ways. Either these matrices are fixed, they are ones on the diagonal and one or minus one outside the diagonal in one position, and then you allow arbitrary powers. Another interpretation is to say that every element, every matrix, is a product of, I don't know, n squared matrices, which have ones in the diagonal and something which you don't bound as equivalent. That's the power. That's the only thing a power does to an elementary matrix. It may move it around and may change its value.
And so the proof uses some K-theory and some playing with Meineke symbols and stuff like this. Just ignore this thing. I have tried to read this proof. For me, this is like a very magic thing. Like you have Orama saying, well, you can reduce this thing to this thing with that many steps, and these two things are completely unrelated, and then you combine like 20 things like this. I don't understand it. There are a couple of other proofs which are a little bit more transparent. They don't give you a bound, they're just existence, but so. Okay, and something about what you mentioned, if you don't care about SO and Z, and if you work over a field, so SO and FP, this is completely trivial. And this is only Gaussian elimination. So for me, this is going to be enough, because for some of the applications, I'm going to use more as this thing.
That's a finite group.
So then
That-
the
that's
point
a-
is that it's 2n square plus 100.
Yeah, but now the point is that the bound is independent on P. And this, from the read theory, it's completely trivial. This is saying that like you have an algebraic group which is generated by one-dimensional groups. Therefore, every element can be written as a product of like fixed number of guys. And this is like dimension arguments. For you, this is like completely like trivial stuff. The bound is the same, I think, even better. I think if you work over a field, you can get 3/2 n square plus something. If you work over a general thing, you have to put 2n square. And of course, you have some additive constant, which is something. There are versions of this result when you replace SO and Z with practically any lattice in an arithmetic group, provided that you have enough unipotents. So any results about bounded generations for high rank lattices are okay if you have unipotents. If you don't have unipotents, forget it. It's like nothing is known.
What about reducing not mod of prime but mod of composite? There are many applications in which that.
It's exactly the same thing. If the image is finite, then everything is trivial. Okay, you can play by hand. It's essentially any composite is a product of primes, or just ignore the radicals and stuff like this. For product of primes, maybe in each prime you have to specify the order, but you have only finitely many possible choices for order, so you get a bound immediately. It's going to be worse. It's going to be exponential in n. I don't care. Just getting a bound is trivial. Just getting a good bound is a little bit hard, but not too much. Okay, so as Avi said, like I'm not really going to care about bounded generation. I'm going to care about some kind of uniform elementary generation, which is the following. I'm thinking about a group of the form SO and R, where R is any ring. And I'm asking the question, is it true that any element can be written as a product of elementary matrices with something of the diagonal, I don't specify that this thing is one, of fixed size? okay, I put it in a different way. I just said I want to have some subgroups, but in many cases, like you want to make sure that your subgroups are much smaller than the big group. So I don't really want to say every element can be written as 20 elements from the group itself. That's true, but it's completely useless. I want to make sure that my subgroups are very, very small. And in practical case, I just pick the root subgroups, which are like.
You don't restrict the order.
No, okay.
You could, but
If I fix the bound, if I fix the rank, it's the same thing as.
you have a finite number of subgroups hi which generate the whole
Yeah.
group, and then you don't
Yeah.
really about the order.
So essentially, the difference between this and bounded generation is for groups like SLN FP of T, where the root subgroup is not finitely generated. You cannot take powers to generate the whole root subgroup.
So in some sense, this is reducing the bounded generation of G to the bounded generation of the HIs. So if you have if each of the
No.
HIs is boundedly generated, then you can.
Okay, if each of the HIs is boundedly generated, I'm going to have that G is boundedly generated. Yeah. But in some cases, HIs are not going to be boundedly generated, but they're going to be something small so that I can plug the representation theory in it. But in most cases, HIs are going to be abelian, because I cannot do representation theory for non-abelian groups. That's at least for me.
But what you will have available is the ability to add all of HIs generating if you have a relative Kazhdan constant now from before. So there is a way to take, just some small generating set, let's say, of the HI and replace it by all of HI if you have a relative Kazhdan number.
What is this GI? Is in the union of HI or?
Okay.
It's bad HJ.
Okay, this have to be J.
But and the union, I want to see the indices. So union over.
So I take
I
the.
less than G or.
No, I take the. Okay, this is saying that each G is in one of the H's. I'm not specifying which one.
The HI is a finite. It's H1 till HK or something like that.
No, this is the whole union. I'm just saying each.
I mean, are you thinking of an infinite number of subgroups? Or
No, everything is finite. Sorry.
So what should you write there instead of GI is an element of union HI?
GJ.
GI is union of HJ, where J goes from 1 to n.
So.
From 1 to small n, which is not capital N.
So it does not depend on the index of the J.
Yeah. I'm just saying
You
each
take
of.
all the GIs from the same set.
Yeah.
Okay,
Yeah.
Thank you.
And the set is just union of subgroups. And I'm saying I want to write an element as a product of guy from here, one of these subgroups in any order I want. And the nice thing is that if I have a finite ring, not any finite ring, I have to specify some conditions, but they're extremely mild conditions. Then if I take a group of like the analog of SL3R, so I have to be a little bit more careful what the group is, but like that's the group you think it is. Then every element can be written as a product of, say, like 50 or 70 elementary matrices.
So EL3 is everything that's generated by the elementary matrix.
Yeah, okay, that's the precise definition, but okay, it's some definition. Okay, so I put nice because I was a little bit lazy and didn't want to check this thing for any finite ring. I'm pretty sure it's probably true, but it's going to be a mess thing to prove. So it's true for any finite commutative rings, it's true for matrix rings, it's true for products. You have to be careful like if it's true for anything, but like I just don't want to take some kind of messy radicals and extensions and just go there. I'm not going to apply to a lot of crazy things. So I'm going to apply to essentially matrices, where you can prove it just by hand. Okay, so something which I want to mention is that this is a very difficult question, even if your group is relatively small and like you understand it. For example, for the group SLNZ adjoint X, it's completely open whether you have this property or not.
What are the H's?
H's are like all the elementary matrices with any polynomial of the diagonal. So this statement is false if you replace Z with the complex numbers by some kind of elementary reasons. So it's a very tricky question whether like you have it or not. This is it's not really a field theory. It's not really okay. Nobody knows what exactly this thing boils down to. What is known is that you can reduce SLN to SL2, I think. But the question is like, can you write any matrix in SL2 as a product of fixed number of error matrices, provided that you have a big enough room to like play around? And this is unknown. Okay, so that's all the background I need. And now let's compute some Kazhdan constants and like let's do some examples. And the examples are going to be essentially these groups. You can easily replace like FP with Z, so you can work with really get results about property T of big groups, but I'm lazy. I don't want to use complicated boundary generation. I just want to use like a simple form for over field, which is relatively elementary. Okay, so how do you do SON FP when we fix n and we let p go to infinity? So what we do is we take SL2Z semi power Z square and map it onto SL2 SLN FP by essentially take this 3x3 matrix and just put it in any possible way by choosing a different indices how to embed it. And the rest you complete with identity. Okay, so the previous one of the previous things gives me some kind of bound for the relative Kazhdan constant of this semi-direct product. So I can combine them, and this tells me that I can compare the Kazhdan constant of SO and FP with respect to the set of all elementary matrices with plus or minus 1, and Kazhdan constant of the same group with respect to all elementary matrices with anything of the diagonal. And the reason is that this set is inside the union of like the images of Z square. Every elementary matrix can be extended, and it's part of like some kind of 3x3 block where like this in the 3x3 block you have SL2 semi-direct product something, and this is the elementary matrix is in the bigger part.
So it really is similar to zigzag, right? In some sense, it's like.
But just to make sure, maybe you should draw a picture. Right?
Okay.
The way you are putting the 3x3 matrices, they are all symmetric, always in symmetric position, so that you can complete it to diagonal.
Yeah.
Yeah.
Okay. So okay, let's.
Draw a picture so that you see how you embed the elementary matrices inside.
So okay.
Replace it with a graphic smaller degree because the things are expanding generally.
Okay, so what I do is I take this elementary matrix, I just pick another one here, and this is my group, which is going to be SL2 sitting here, acting on FP cross FP sitting here. And the relative Kazhdan property tells me that I can throw the whole union of this abelian group in the generating set. Okay, I'm going to throw only some piece of this subgroup, which is this one. I just don't want my union to be very messy and like not like manageable. And you get some constant. The constant is independent on p. That's the important thing.
So in the original Kazhdan proof, we were doing more or less the same without a bound on the relative Kazhdan constant. Just
What is the original Kazhdan proof?
prove that SLN well help you, don't you?
No, okay, so the original Kazhdan proof is in some sense exactly in this picture, but you don't do it over Z, you do it over the real numbers. Over the real numbers, you have boundary generation for obvious reasons. You have this kind of relative property T. Of course, he didn't use like this kind of quantitative version of.
He didn't have the quantitative bound.
But the relative property T was known, and he was using something which is exactly like this. Okay. Okay, so I said what EN is, and then a boundary generation is one way of saying that if I take the generating set EN, which is like all elementary matrices with something of the diagonal, if I take a bow of radius like 2n square, I'm going to get everything. This is exactly the same thing as saying that every matrix can be written as a product of 2n square elementary matrices in some way. I don't care what is the order. And so when you combine them, so you can compare this thing where you replace, you put above certain radius here, which is everything.
I don't understand your first quality.
This one or this one?
There's a first one.
This one.
Is it that's zero positive? I mean, the generating set on the left hand side is bigger than the.
Yeah, the generating set on this side is bigger, therefore I have to divide.
But just by a constant.
That's the whole point. Whenever you increase the generating set, the Kazhdan constant goes up. But the statement here is doesn't go up too much, so you can go in the opposite direction by dividing by something.
Something that's a bit strange is that you only use z square, z2 in the embedding.
Yeah.
You don't use SL2z. When you embed this group into SLN
Yeah.
Z, you only use the only matrices with the SL2z part is identity.
No, in the generating set I put everything. So okay, so when I do this thing here, so this falls from the realm where it says that if I have a bunch of subgroups and the normal subgroups in them, I can replace Kazhdan constant with respect to the union of the generators with respect to the union of the subgroups. So in each of these guys, I pick a generating set which consists of something here, something here, something here, and something here.
So then the generating set will have all these submatrices with SL2z semi-direct further.
So then the union of the generating sets is going to be all elementary matrices with plus or minus 1, because this is elementary matrix with plus or minus 1. This is also like elementary matrix at some other place. So I'm going to have a lot of repetition when I take this union, but I don't care.
The final generating set you have only elementary matrix. That's the matrix.
Okay.
What Avi said is true, that at the end, the generating set for SLNP will be only...
Yep, that's what I'm going
With plus minus 1.
with plus or minus 1, yeah. So this allows me to go from elementary matrices with plus or minus 1 to any elementary matrices. This tells me I can go from any elementary matrix to everything by just putting some constant which depends on n. However, this thing is practically 1 because this is the whole group. And you combine this thing, and okay, this looks a little bit ugly, sorry about that. So this result of Yehuda saying that the Kazhdan constant of SLNFP with respect to the elementary matrices with plus or minus 1 of the diagonal. So this is a finite set with something like n square elements is bounded by 1 over 40n square, completely independent on P. And actually, like in this argument, you can replace FP with Z, and everything is more or less going to be the same. It's just a little bit more involved argument. So this is not really the exact answer. You can improve this thing to 1 over square root of n times a constant, but this is the idea. And if you want to improve it to 1 over square root of n, it's the same thing. You just have to be a little bit more careful.
This already gives expanders.
Yeah, this gives that's the whole thing. This gives you expanders, and this gives you expanders with
Because there's no P on the right.
because there is no P on this side, and this gives you a very good control over the expanding constant. It's not the best one, but it's like reasonably good. If you improve this thing to 1 over square root of n, it's going to give you like essentially the best possible control. Okay, so let's beef this thing a little bit, and let also n goes to infinity. So now I'm going to be a little bit lazy, and I'm going to do SL3n. So I'm going to assume that n is divisible by 3 for technical reasons. You can easily bypass it. And essentially what's going on is I'm going to use like block decomposition of a 3 by 3 matrix, 3n by 3n matrix into 3 by 3 matrix with blocks of size n. So I'm going to get the group SL3n over Fp, and I can think of this as a group of 3 by 3 invertible matrices over matrices of size n over Fp. And that's not incorrect, you're just block decomposition. Okay, you have to verify that these two groups are the same because they have slightly different definitions, which means that you have to do something, but that's easy.
Can you say again what EL is? I'm sorry.
EL, think about GL of non-associative ring. So you just take all invertible matrices, but not all of them, everything which can be written as a product of elementary matrices. Okay, I think about it as SL, but like if the ring is not commutative, like I really don't want to put SL3 of this thing because that's going to be like really cheating and everybody's going to start screaming.
So E is elementary.
Yeah. So in general, if the ring is commutative, ELN and SLN are practically the same. It's a non-trivial result that they're the same in some specific cases. There are many cases where they're different, but from my viewpoint, they're the same. Okay. Now the ring of like n by n matrices over Fp is generated by two elements. That's very easy to see. You just pick two random matrices and they're going to generate the ring as a ring. This is like a very weak statement. And as I said, this group has some kind of like bounded generation property.
That's by your previous result.
That's essentially the previous result. This really says that every 3n by 3n block matrix, 3n by 3n matrix can be written as a part of fixed number of block elementary matrices. And this fixed number is independent on the size of the field or the size of the blocks.
This is just a nice ring. Matrices over field is a nice ring. So
It's nice according to my definition, of course. Like for me, it's like, if I have to state some theorem, I say it's true for nice things and like go and figure out what nice is. And now you can essentially repeat the same argument. You do the same kind of embedding of like analog of SL2, of the semi-direct product SL2, this one, because this is exactly the same picture. And this allows you to compare Kazhdan constant of SL3 and FP, which you think in this way, with respect to elementary matrices with the generators of the ring. And
the A and B are the two generators.
and B are the two generators I'm talking about. And I can put like all elementary matrices, block elementary matrices here. The next step is this kind of like block bounded, block uniform generation, uniform bounded generation. Again, the same inequality. You combine them, and you get some generating set, which is like essentially this one. And the Kazhdan constant is independent on n and on p.
Did you get the first inequality?
This is, okay, just a second. This is essentially the same thing as here, but you replace Z with matrices. And you use the same result about relative property T. The same result is like, it just assumes that the ring is associative and generated by a small number of elements. That's the only thing you need to care about. Of course, you have to play a little bit with the constants. Maybe, no, I don't. I think I put enough room here, so.
The size of the generating set depends on n?
The size is completely independent on anything. The size is like 20. Because what I'm doing, I'm taking 3 by 3 elementary matrices. So I have like 6 choices for the position. And for each of them, I have like one of 3 elements up to a sign. So it depends. Like it's probably 40 if you have to count the inverses. If you don't count the inverses, it's 20. And of course, you can shrink it a little bit if you are very greedy and like want to optimize it. I think I can get it down to 4. I don't know how to get it with 2 and 3, but okay. And this is something which I don't really care about. So the generating set is the following. I pick 2 generators of matrices as a ring. And now I just look at the block matrices where of the diagonal I have either one or one of these 2 generators. That's my generating set. So here I'm really careful and I don't want to state this theorem as property T for some infinite group. I can state it, but it requires some work.
Well, that's why I'm asking, because it feels like you're saying something about the unitary dual of SL and Z being uniformly bounded away irrespective of n.
with respect to some generating set.
Yeah.
With respect to a suitable sequence of generating sets. That's the correct statement. So, okay, if you want to see a fancy result, this is like what I'm going to go into in a moment. This is a theorem of Ershoff and Heikin, which says that if R is finitely generated ring, EL3R has property T. That's it. It's a really nice theorem. And okay, I'm not going to go into a proof. I'm going to sketch it in a moment. Excuse me?
What's the difference between is and is?
So if R is finitely generated ring, so okay, you need to assume that the group is finitely generated or something. You just need some kind of Mayotte condition, yeah?
Could you rephrase all these inequalities in terms of the calligraph and expansion in a combinatorial way?
Of course. I mean, that's an eigenvalue thing.
So essentially, this thing is saying that if you take this generating set, and if you look at the K-graph of SLN, SL3.
I'm speaking about the proof, the breaking up the graph into components and expansion of components and so on.
No, I don't think so. I'm really using the group structure at some points. So whenever I'm using relative property T, so okay. Okay, maybe I can do it this way. Okay, that wasn't a good idea. So I think this is a point where I really have to use a group structure. I cannot phrase this thing completely bypassing the group structure.
It's not like replacement product or something?
This is some version of the zigzag product. The problem is that I'm going to use zigzag product at like in the same graph in several different places with respect to several different generating sets. And probably I can phrase it in completely in the graph theory language, but it's going to be a painful thing to do, and I don't want to do it.
But you could say that you have, you don't forget about the graph, the group structure when you look at the calligraph. You could say that you have a big set of generators that expand, that says that the calligraph with respect to this set is expanded, and then this set is generated, expanded by smaller sets.
Okay, I can say that this is equivalent in if in the Kerry graph I have a lot of subgraphs which are expanders, I can replace them with complete graphs. But okay, I haven't tried to like remove the group theory from this one, and the reason is I'm doing group theory, so this is completely insane idea, at least from my viewpoint. Like, take a group theory proof and like remove the group theory from it and like obtain something which is like no matter. I have no idea what. Okay, so up, yeah. You can replace it. It's not too difficult. It's just an extra step which I'm raising. I don't want to put it on the slide. Essentially, one easy way to do it is to say, if you have like 3n plus 1 by 3n plus 1 matrix, every element there can be written as a product of like 5 matrices which are like in 3n by 3n blocks, which are in suitable places. That's not so difficult. So you can take this one and just replace SLN with any high rank group and so on. It's just technical nightmare.
So n has to be bigger than sweetness.
Okay, you have to be in the high rank case.
Yeah.
So in some sense, like if you're in rank 1 case, you have expanders in one rank group, but like the proof is completely different. You cannot do it using property T. You have to use some number theory at some point. And like these methods are like completely perpendicular to number theory.
Do you have better lower bounds on Kazhdan constants for generating sets which arise as projections from SL3C?
You mean here?
Yes.
What do you mean a better lower bound? Okay, this is a constant. So for me, it's like all the constants are equivalent. So essentially, this is like it's around 1.
They are not Ramanujan graphs.
Yeah, okay, you cannot get Ramanujan graphs. There is no chance that you can get Ramanujan graphs using this machinery. This is like very weak machinery. It's like you cannot get close to Ramanujan graphs. There is no hope you can do it. So you're not really getting the Kazhdan constant on those. You're getting something which is like close to it, but not exactly. Close by a constant factor. I'm pretty sure you can improve this 1000 to maybe 100, maybe 150 if you spend like a lot of time doing it. I just don't want to do it. It's too difficult and not very interesting. Okay. Okay, so now this is like what I wanted to talk about. So this is a very nice geometric way to prove things related to property T, which have been around for several years. So I think this method was developed by Di Morea and Januszkiewicz about 2002, 2001, I'm not sure. But they said, oh, no, this is not ours. This goes back to Garon from the late 70s. And like, I have no idea like who is the real guy behind it. Of course, at some point I tried to read their paper and I couldn't read it, and like I learned it from Ershov and Haikin last year. Okay, so let's start with a Tor example, which is like essentially one of the smallest examples of a group without property T. So for me, from this viewpoint, the smallest group without property T is the infinite dihedral group. So you have a group which is generated by two elements of order 2, no other relations. Okay, and this group does not have property T for relatively elementary reasons. So what I'm going to do is I'm going to construct your representations with almost invariant vectors without invariant vectors.
So what is the multiplication for the group?
So
it's like words, but whenever you see two A's next to each other,
this is the infinite. So this is, you have Z, and you on the top you add like a refraction, which like.
So A and B are just symbols.
Yeah, A and B are just symbols, and like you take all the words on A and B, and essentially the only words which are out is A, B, A, B, A, B, A, B, and like you go for some time. Okay, what's an easy representation of this group? You can build a two-dimensional representation by just picking two lines in the plane and take two refractions with respect to these two lines. And like the refractions are of order 2, so you have a representation of the infinity dihedral group. Okay, so you take these two lines and you pick a vector exactly here in the middle. And so this vector is A sends it to here, B sends it to here. If the angle is very small, this vector is moved a little bit by every generator. And if you compute it, you get that this vector is 2 sine phi almost invariant with respect to the generating set consisting of A and B. However, this representation does not have any invariant vectors by obvious reasons, like essentially A times B acts as a rotation and like doesn't fix anything. And this really tells you that the group does not have property T. For any epsilon, I can take a small angle, I can build a representation with epsilon invariant vectors, but without invariant vectors.
The reaction of A on this just flip the direction.
A flips with respect to this one, B flips with respect to this one. Just the obvious representation. Okay, so what this thing is saying, if I have a group which is generated by two subgroups, say G1 and G2, so in this case, the two subgroups are like 1A and 1B. They're tiny, but they generate the group. So if I want to get property T, somehow I have to make sure that like their fixed spaces are not too close together. So somehow I have to bound the angle between the two fixed subspaces. Okay.
Well, you have to think of these subspaces as sitting in some bigger space.
I have to bound this angle in any representation of the big group. Because in general I can, let's go to the next slide. So assume that I have a group which is generated by elements of order 2. this is like a technical reason. It was like I just don't want to mess with the big thing. So each element of order 2 has some kind of fixed subspace. And if I have a representation, this representation has no G-invariant vectors if and only if the intersection of this subspace is trivial. Because everything which is in the intersection is just fixed by everything, by all the generators, and therefore by the whole group. Okay, so if I have a generator, this generator moves any vector by something which is more or less the distance from the vector to the fixed subspace. Okay, you have a factor of 2, ignore it, there is no big deal. So if I want to prove that the group has property T, what I have to do is I have to prove that for any representation, if I have any vector which is close to all of these fixed subspaces, the vector has to be close to the intersection. And I have to quantify this thing, and I have to make a quantifier independent on the representation. I have to say, if a vector is like a distance 1 from each of the subspaces, then it's a distance at most like 70 from the intersection. This is going to be equivalent to property T. Okay, so now let's start talking about angles and like some geometry. So there are several ways to measure angle between two subspaces in a Hilbert space. Essentially, the only thing which is like non-trivial is what to do with the intersection. Okay, so in this example, I'm ignoring the intersection. So this definition is, if you want to have like a motivating example, this is angle between two planes in the three-dimensional space. So you take these two subspaces, you take the intersection, and you say, okay, let's look at the vectors which are in each of the subspaces, but are perpendicular to the intersection. I don't want to get like close to the intersection because things get ugly there. And I look at for the smallest possible angle between them. Okay, an equivalent way to define this with this for me, which is slightly better because I can generalize it. I can look at the addition defined on the exterior direct sum of h1 modulo the intersection and h2 modulo the intersection going to whatever it goes to, h modulo the intersection. And you compute the norm of this operator, and like it's more or less 1 plus cosine. So I can define the angle not using this definition, because this definition is, it's nice, it's geometric, but I cannot formalize it. It's not very nice to work with it because you have to use geometry and I don't know how to do geometry. So I can say the angle comes from the spectral gap of this operator, which is essentially this one, and I'm looking for the spectral gap near square root of 2. And I have to talk about spectral gap because if I have intersection, square root of 2 is inside the spectrum. So I'm not looking for the supreme of the spectrum, which is the norm of the operator, because here I make the norm by just quotienting the top eigenspace. But I'm just looking for the spectral gap. Okay, so all these definitions are equivalent. You can think of this as a motivating definition. This is the definition you want to work with because it's nicer from linear algebra point of view. Okay, I have an operator on some Hilbert space. Okay, it's actually not an operator. Okay, so what you do is like you multiply it by its transpose. And so you just take the transpose, you combine them, you get an operator on this thing. And like it's a self-adjoint operator, its maximal eigenvalue is 2, and now you look at for the spectral gap near 2. Okay, that's exactly what you're doing. It's okay, you caught me. I like to cheat on the slides. Okay, so there is some kind of like tiny font which says that this is a very nice definition, but it gives you a very strange results if one subspace is inside the other. And you can work it out what it gives you. It gives you an unexpected answer which is not geometric. But okay, so what? Okay, now you can take this definition and say, okay, like why restrict ourselves to 2 subspaces? We can do it for 5 subspaces. We can call it angle. It doesn't have any geometric meaning. I don't claim that there is any geometry behind this thing. But you take exactly the same definition. You take n subspaces. You take this operator, which is again the addition, And you say the norm is something which is related to the cosine. And you have to normalize it in the correct way in order to get cosine between 0 and 1.
It's more or less, I would assume, I didn't read it, but that for two guys, for two subspaces, you look at pairs of vectors appropriately for getting the intersection, and you see how orthogonal they are.
Yep.
And here you take a representative from each of the subspaces, and you look at the system of vectors, and you see how orthogonal this, how close to orthonormal this is.
So if you want to do it, that's the other definition. You take a bunch of vectors which are in each subspace perpendicular to the intersection, and you compare the norm of the sum with the norm of with the sum of the norms, and you normalize it in some way.
So that's how close to orthonormal this system of vectors is.
Yeah.
How far?
Okay. So yeah. Okay. So something which is like more or less obvious, if you work in finite dimensional space, then the angle is always positive. Essentially, the only way to get an angle 0 is that if you have intersection, but we are modeling out the intersection. And then you use some kind of compactness, like you have the spectrum is discrete, you always have a spectral gap and stuff like this. In general Hilbert space, you may not have a spectral gap and the angle may be 0 for a non-trivial correction. Another thing I want to say, which also goes back to this definition for 2, this is not a continuous function even in the finite dimensional case. If you fix the dimensions of h, h1, and h2, you can think of the angle as a function of a product of two Grassmannians. It's not going to be a continuous function because when you have two subspaces, when they get close to each other, the angle goes to 0. But at some point, they have an intersection, and now you're starting modeling out by this intersection, and the angle becomes something else. Essentially, what you have an eigenvalue which goes to 2, and you say, okay, but we're looking at the spectral gap, so the spectral gap goes to 0, but once it gets to 2, like the spectral gap, this is not the relevant one, you're looking for the next thing. Okay, so an equivalent way to think about this angle is the following. This is exactly what I need. Is if I have a bound for the angle, this is equivalent to saying that if I have a point which is close to all subspaces, it has to be close to the intersection. You just play a little bit with inequalities and like some very easy linear algebra. Okay. So where is the next thing? Okay. Okay, so now we have to do some representation theory in order to control these kind of angles. And let's do like 2 Tor examples. Again, I'm going to skip it or skip the proofs. Suppose that I have like 2 elements of order 2 which generate not the infinite dihedral group, but a finite dihedral group. Then when I take any representation of the finite dihedral group, when I take their fixed subspaces, the angle cannot be very small. The angle is always more than pi over k, where k is the order of the dihedral group. Okay, so what is the proof? So this is the same machinery as like with Kazhdan constants or anything. Like first you check that you don't need any representation, you can do it only for irreducible representations, and then you say, okay, I have this small group, I know all irreducible representations, let's go over the list and check it. And you just go over the list.
So this 2x2 matrix set whose entries are roots of unity of order k.
Essentially that's a trivial check, it's like very easy, not a big deal. Okay, so I'm going to apply it for something a little bit more fancy. So I'm going to take not 2 elements of order 2, but 2 elements of order p. And they're not going to generate a dihedral group because I don't have a dihedral group generated by elements of order p. I'm going to have a Heisenberg group. So a Heisenberg group is essentially a group of order p cube where like the commutator is central and like you have something small.
It's upper diagonal 3x3 matrix.
Upper triangle, yeah, over.
The diagonal
Yeah.
elements mod p in the
Yeah.
3.
Yeah, exactly. Again, this is a small group. You can take all the representations. You can just go over the representation and check what is the smallest angle between the fixed subspaces. And what you get is that the cosine of the angle is always less than 1 over square root of p. And when p is big, this means that the fixed subspaces are practically perpendicular, which is not an obvious thing. Like immediately, but like just it comes from the representation theory. Again, this is some kind of representation theory which is like very easy. Like you don't have to use any fancy thing to do it. Like you just say, okay, this is a small group, just use brute force and let's do it. Okay, so this is like the only representation theory I'm going to use. Okay, so now let's play with like another Tor example. So suppose that I have a tree-generated Coxeter group. So this is a group which is generated by 3 elements of order 2, such that like the product of any 2 of them is of some fixed order. And the question is like, you have a group, you have a family of groups, when do you have property T? And the first thing is, okay, like, these groups are classified, let's just take the classification and check it. And looking at the classification, there are 3 things which are equivalent. The group has property T, the group is finite, and 1 over some of the mij's is more than 1. So this is like, this is equivalent to being finite. These 2 things are relatively easy to see. So if the group is not finite, you just build a representation on some hyperbolic space and like you just play a little bit, and you get properties. Okay, so what I want to convince you is that I can go from this direction to this one without going through here. And without using any representation, any like classification of Coxeter groups, just linear algebra. Okay, so what do I have here? I have a group generated by 3 elements of order 2. I take the fixed subspaces for each of them. So I have 3 subspaces in a Hilbert space. I have bounds for the angles between any pair of them, and I want to get to say something. So this is a lemma which is a very key to the whole thing, and the proof is just inequalities with projections, essentially 5, 6 lines. Suppose that you have 3 subspaces in a Hilbert space, and you know the angles between them. And if the sum of the angles is more than pi, then you have this kind of inequality. If you have a vector which is close to each of the subspaces, it has to be close to the intersection. So you can quantify these things. So it's like the norm is some kind of like constant, and the constant depends only on the angle. So if you go down to the proof, what you see is the following. Essentially, the worst case is the case of 3 planes in a 3-dimensional space. So you have 3 planes, you have the 3 angles between them, and you're looking for the vector which is like, say, a unit vector which is as close as possible to each of them. And you just optimize it and write it down and like get a bunch of inequalities. Okay, you have to prove it. This is not a completely trivial thing, but like you can do it. So I really need this condition. I need the condition that the sum of the angles is more than pi, because otherwise I cannot build this picture in the 3-dimensional space. Simply, like, there are no 3 planes in the space such that the angles between them are equal to this thing. If this condition is not satisfied, it's very easy to see that there is no bound for the angle. For example, if the condition is equal, if this thing is equal to pi, what I can do is I can take a triangle, a Euclidean triangle, and put it on a very big sphere, a very big radius, and then take a cone over it. And so the angle between the sides of the triangle is going to be exactly almost the same thing as the angle between the sides of the cones, which are like above these 2 things. So the 3 planes are going to have more or less the same angles, but I'm going to have a point in the middle of the triangle which is like very close to each of the sides, but it's very far from the center because like the cone is like very sharp. Okay, so
these are examples, and you are going to show us how these distances from subspaces allow you to move.
Okay, so so this is a geometric lemma, and so in the next couple of slides, I'm going to convince you that this geometric lemma practically implies this thing for 3 generated Coxeter groups, and I'm going to extend it to a more complicated things. Okay, so what I'm going to look at is the following. I'm going to look at a configuration of like n subspaces in a Hilbert space which satisfy some conditions. So what are kind of conditions I'm going to impose? I'm going to impose conditions like of the previous type, which I just saw. Say, for example, I take the first, the second, and the third subspace, and I say I have a bound for the angle between these guys. And I just put some kind of bounds for some subsets. I'm not specifying which one. Okay, I can impose some extra conditions, which are saying, say, if I intersect the first and the fifth one, the intersection have to lie in the second one. So, okay, I impose some kind of conditions. And I ask the question, is it true that when you go over all possible configuration of subspaces satisfying these conditions, I have a uniform bound for the angle between all of them? And I say, okay, like if this is true, I should be able to prove this thing geometrically, because this is a completely geometric statement. And okay, I call this thing, these conditions like nice. And again, I have to say that in this definition, I'm not specifying the dimension of the HICs, the dimension of the ambient Hilbert space. I'm saying just anything. However, it's not too difficult to see that you can restrict yourself to some finite dimensional situation. Essentially, you're working with one vector, and you start taking projections of this vector to all possible intersections. And like you can assume that they span everything.
Yeah, so it depends on n.
It depends on n, but like if you fix n, this you don't have to go to arbitrary Hilbert space. You have to work only in some fixed dimension of Hilbert space. So if I give you the condition, and like you can program a computer to check whether this thing is good or not. It's going to take you forever, and like the computer have to do some kind of crazy optimization in some huge dimensional space, which is, I'm not sure whether it's feasible or not, but okay, it's not like extremely difficult problem from this viewpoint.
So the subset J can, the size of J can be n minus 1?
The size of J can be anything. I'm not saying what is J is. I'm just saying, okay, I'm imposing conditions of this type. How many conditions, like you're going to see in a minute why I'm putting these kinds of conditions. So typically, I'm going to want J to be small. Because I'm going to, when you translate this thing to group theory, this tells you something. And like this tells you some kind of like, you want to do some kind of local representation theory. And local means like how big J is. So essentially, the previous realm about the three subspaces tells you that if you have the bounds for the three angles, and the sum of the bounds is more than pi, then you have a good correction. You have a uniform bound for the angle between the three of them, which is independent on the Hilbert space, independent on the configuration, just some kind of like global stuff. Okay, so why do I care about this thing? Suppose that I have a group which is generated by some subgroups. Okay, let's assume that the subgroups are finite. I just don't want to go into big mess. And I take a representation of the big group. So in this representation, I can take the fixed points of each of the groups, subgroups. There are some subspaces. And now I have two types of restrictions which are coming from the representation theory of the group. So if I understand the representation theory of the group generated by, say, a pair of GIs, this really tells me a bound for the angle between the corresponding fixed spaces. If I want to bound like the angle between 20 HIs, then I have to take the representation here of the group generated by the 20 subgroups and I can understand it and do something. But okay, if I understand this kind of representation theory, I can use it and translate it into some kind of bound for the angles. The second condition is saying if I have one group which is inside a group generated by 5 of the others, this means that when I take the intersection of the fixed points of these guys, it has to be inside the fixed point set for this guy. So this is the second type of condition. So essentially, this tells me that if I have a group, from some kind of like local representation here of the group, I can build a lot of conditions, and I can impose some conditions on the configuration of subspaces. And the key fact is that if these conditions define a good arrangement of spaces, so where I have a global bound for the angle, this implies that the group has property T. And this is like essentially very easy. Like there is nothing in it. You're just translating one definition to another definition.
So sometimes the local conditions are sort of Kazhdan property T for these pairs or small subsets because you get good angles. You are saying that good angles are more or less equivalent to
very good bounds for the Kazhdan.
Good bounds for Kazhdan.
It's you need not only property T, you need a very good bound for the angle.
They are finite. You always have property T, right? So
Well, I'm not assuming that the group generated by any pair is finite, but okay. You can drop the conditions that the groups are finite. That's not a big deal. You can couple this thing with some relative property T. It's just I just don't want to do it. But okay, so I have 15 more minutes. Okay, I can do like one easy example.
Okay, you can go a little bit over time. We ask lots of questions.
Well, go ahead, ask more. So the easy example is like essentially let's try to do the same thing in the smallest possible setting. You have a bunch of subspaces, and you just know bounds for the angle between any two of them, nothing else. And the reason is like this is like the smallest representation theory I need to use. Like any angle between two of them means representation theory of the group generated by pairs of GIs, nothing more. Okay, so if we can find a sufficient condition for this correction to be good, then this implies that we can get property T for some groups. And this is going to be a very big class of groups because I'm going to say any group which is generated by a bunch of finite subgroups such that any two of them generate something reasonably nice is going to have property T. Okay, so what was known is essentially like Dimar and Januszkiewicz, which more or less started this machinery. They proved that if all the epsilon ij's are very, very small, and they're definitely very lazy about this thing, they just put some kind of like.
So this is like they're almost really completely orthogonal. So you get the angle between the whole collection just by Gram-Schmidt or something like this. Yeah, by.
Okay. Yes.
Yes.
Yeah. That's what they're doing, and they're like say, okay, like we can like make this thing quantified and say, okay, they don't have to be perpendicular, they can be like almost perpendicular, and we don't care about what almost means, so let's just get any bound. So what Misha Ershov and Andrei Haikin did is they said, okay, let's look at this proof and like we can improve it a little bit, and they improved this exponential bound to something like 1 over n minus.
I would expect something like Gram-Schmidt corrections. You just
yeah, that's
one by one, right?
Yeah, okay, that's okay, you're getting there. So they also like did the case n equals 3 with some kind of completely, at least from my viewpoint, insane machinery, and say essentially the sum of the angles have to be more than pi. Using like 3 pages of like crazy computations saying, oh this system of like 4 nonlinear equations has a solution in this case and something like this. And I really told them, okay guys, you're not proving the right theorem. This is a wrong result. Like you're proving something using like strange machinery, and you're getting something which you cannot like understand what it is. And of course Misha said, okay, like what is the correct result? And I just put the following thing on my board when he visited me at some point. So there is only one thing which is like natural here. You just take a matrix and you put ones on the diagonals, put like minus cosines of the angles of the diagonal, and if this matrix is positive definite, this has to imply that everything is nice. Okay, and there should be a bound for all the angles in terms of the properties of this matrix, in particular which is independent on the Hilbert space or on anything. And actually what it turns out is that, okay, let's translate this thing in a geometric language. Suppose that you have n subspaces, you have bounds for any two of them. So the correction is good if and only if there exists an n-dimensional spherical simplex such that the face angles are exactly these guys. And this is more or less the same as the condition, like you have a spherical triangle if and only if the sum of the angles is more than pi. This is translation of the statement. And the existence of a spherical simplex is known to be equivalent to this kind of like positive definiteness of this kind of matrix. So the statement is if and only if one direction is very easy. Like if you don't have a spherical simplex, forget it. There is no chance you can do it. Okay, I'm going to cheat with the proof because I'm lazy. Okay, so the first observation is that there is the worst case, and there is an obvious candidate for the worst case. This is when you have like a hyperplanes in some kind of n-dimensional space. Okay, so what's going on if you have a hyperplanes in n-dimensional space? You can replace each hyperplane by its normal vector. You can take, the angles between the normal vectors. This is exactly this matrix. This matrix gives you the volume of some simplex up to some square. Actually, the determinant of this matrix gives you the volume of the simplex. You have an upper bound for the surface area of the simplex, because like everything is unit. And therefore, if you take a point inside the interior of the simplex, it has to be far from at least one of the sides. And you can quantify this thing if you want. So this is the idea. Actually, the precise theorem is that any reasonable bound you can think of comes from this kind of configuration of n subspaces. And in general, you just have to do a very clever induction in order to justify that this is the worst case. And the induction is essentially analog of Gram-Schmidt. You just do it by 3, and then you start, you go to the intersection with one of the subspaces, project, compute all the angles, and so on.
This was not known?
This was not known.
Yeah, it looks like geometer should have.
Okay.
In fact, it makes sense to even define, I don't know if it makes sense, but with hindsight, to define the angle between many subspaces in terms of the determinant of as a minimum determinant of all choices of one vector for each.
This is equivalent to my definition. Okay, so what's the application? This is like essentially, it goes back to Dimitrov-Januszkiewicz because you have to be a little bit careful in translating. If you have a group which is generated by a bunch of finite subgroups, and if for any pair of indices, the group generated by them has a property T, and you have a very good bound for the Kazhdan constant, then the big group has property T. So essentially, the only thing I changed is like I said, okay, what is very big, and okay, so in the terms of Kazhdan constants, like the condition is very messy. You cannot really, you can translate it, but it doesn't look nice. In terms of the angles, you have a reasonably nice condition. Okay, so
can I ask something?
Sure.
This type of theorem and this type of local condition sort of remind me of the theorem of Zurk about inferring that a group has property T from the fact that the flags around every vertex have essentially I as that constant.
it seems similar, but I tried and missioned and I tried to find some kind of like connection, and there is nothing obvious. Essentially, the Zurk's theorem is something about the Kerry graph. You don't see the group structure. You don't see any subgroups. It's very strange condition. It's a the proof. Okay, the proof is not geometric. The proof of this thing is not geometric. The proof is linear algebra. When you do anything like this, okay, what is geometry? That's a very difficult question. But like for me, it's like the proof is linear algebra. You just start using projections and like very easy inequalities and so on. Okay, so let's quickly do 2 applications. So the first application is something which I found like maybe 2 weeks ago, and I'm really proud of it because it's a very nice application. Suppose that you have a Coxeter group. It's relatively well known that a Coxeter group has property T if and only if the group is finite. So if it's finite, it's obvious. If it's not finite, okay, you play a little bit and you produce crazy representation. That's not a problem. The question is like, if you have a Coxeter group, what is the Kazhdan constant with respect to the standard generating set? And this is the statement. You don't need to do any crazy representation theory in order to compute the Kazhdan constant of the Coxeter group. The only thing you have to do is you have to look at the defining representation where the Coxeter group acts as a group of reflections and just compute the constants from there. And that's it.
So the bound that comes from
the bound that
method is
the bound that comes from this representation is exactly the the bound which comes from this kind of game with matrices and eigenvalues, and it's, for example, if you take a random walk on Coxeter group, so take a symmetric group, the mixing time is going to be something, and you can estimate it's going to be like n cube log n. It's not the best one, but it's very close to being the best one. Actually, no, I think this is the best one.
What is the rank of the Coxeter?
The number of generators. So think about the symmetric group. That's the classical example. So for the case of the symmetric group, this was done by Butcher and Dewer-Harp in the mid-80s, I think. And that's the only exact value of the Kazhdan constant for a non-trivial group which I have seen in the literature. And this is like essentially generalize it without using any representation of the symmetric group. You just use angles and that's it. Okay, so.
Sorry, with respect to which generators would it be? That this would be in the symmetric group, it will be the transposition.
Adjacent transpositions, 1, 2, 3, and so on. Okay, so let's do another example. Let's prove that SLN FP T1 adjoint some number of variables has property T. So, okay, I'm going to be a bit lazy. I'm going to assume that P is more than 4 because I don't want to do like crazy stuff, but that's the idea. What you do is you take a group, and inside this group you pick a bunch of finite subgroups. So what is G1? G1 is like all the elementary matrices with multiples of 1 here. G2 is multiples of 2 here, and so on. The only different thing is that the last thing, in the last group you allow not only multiples of 1, but like multiples of the generators also. Okay, so these guys generate the group. There are a bunch of finite groups, subgroups, so you can talk about relative Kazhdan constants. You can estimate them. Okay, so what do you know? If we take any pair of these two groups, they either commute if they're far from each other, like this one or this one, or if they're close to each other, they generate a Heisenberg group. Okay, so this one and this one generate something slightly bigger than the Heisenberg group, but it's equivalent. Don't worry about it. So you can take the representation theory coming from there and translate into this matrix. So what do you get? You get a matrix which is ones on the diagonal minus epsilons on the two diagonals next to it and something in the corner where epsilon is 1 over square root of p. And you open the big books and say, okay, what is the spectral gap, the smallest eigenvalue for this matrix? It's like 1 minus 2 epsilon, and the matrix is positive definite if p is more than 4. So since the matrix is positive definite, you can apply the theorem, and this tells you that this group has property T. In fact, there is no representation theory whatsoever, no boundary generation, nothing. Just some kind of Heisenberg groups sitting there and some. Okay, you can generalize this thing to any Steinberg groups. Maybe you have to increase the characteristic a little bit, but not a big deal. Okay, do I want to go with this one? Okay. So we have some kind of project with Misha and Andrei to generalize their result about EL3R. So we define something which we call group graded by a root system. And our example is essentially groups of free type where you have root subgroups corresponding to the. So think about SLN, and you can think of the elementary subgroups indexed by the roots in a root system of type AN. So for every root you have a subgroup.
No, so you have to say what the root of a group.
Okay, I'm taking a root system which is some subset in a Euclidean space, satisfying some axioms. And for SLN Z, I can say, okay, the root system is like the root system of type AN, which is like plus minus, like 1 plus 1, 1 minus 1. You have and choose two choices for this one. And for each root, which is like, okay, let's do it for SL3. For SL3, the root system is this one, A2. Yeah, and for at each root, I associate some kind of group of elementary matrices. So here I think I put, say, x1 to, the opposite is x to 1. I don't remember which ones are here. So x1, 2. Okay, so this is standard in the Lie theory. So if you have a semi-simple regroup over a field, you can just, you have this kind of root subgroups. Okay, so we generalize this and say, okay, like you don't need to have like fields, you don't need anything here. Just start with some kind of subset in Euclidean space. Suppose that you have a group with a bunch of subgroups satisfying some kind of axioms which like you typically see in groups of free type. So the first one is the group is generated by all these guys. The second one is if you take two root subgroups, their commutator is somehow inside the group generated by positive combinations of these roots. If you can have like roots which are multiple of each other, you have to modify this thing a little bit, not a big deal. And you have an extra technical conditions which I'm not going to specify this thing. But essentially this is saying the group is well connected, like you can go from one root subgroup to another. And what we proved, and this is essentially the same idea, you just look at the fixed subspaces of each root subgroups, you start intersecting them, start bounding the angles between whatever you can, and like just go there and like use tons of linear algebra, and don't even say that you're working with this kind of geometric objects. Then you can compute the Kazhdan constant of the big group with respect to the union of the root subgroups. And it only depends on the root system, on nothing else. And for example, you can take any form of Steinberg group, twist it, untwist it, whatever, over anything you know how to define it, it's going to have property T. Up. Yeah. And I think that's it. Okay, I went a little bit over time, but sorry about that.